Suppose you roll a fair six-sided die until you've seen all 6 faces. What is the probability you won't see an odd-numbered face until you've seen all even-numbered faces? You have 4 minutes. Let's now begin solving this problem. We can begin by approaching this problem like we would any probability question, by counting the number of valid solutions and dividing by the number of total solutions. The denominator is much easier to calculate, so let's begin there. We can think of every instance of seeing all 6 faces as reducing down to the string of 6 unique digits corresponding to when we first see that digit. For example, if we see 2, 2, then 4, 6, 1, 1, 3, 5. Only on this roll will we have seen all 6 faces. However, as we can see, we have duplicates. However, for the intentions of this problem, this sequence reduces down to 2, 4, 6, 1, 3, 5, which also happens to be a valid solution to this question because we see all of our even numbers before we see all of our odds. So now, let's begin to enumerate the number of total solutions. This sub-question simply reduces down to the number of ways that we can order the 6 distinct faces. And as we know from our counting arguments, this is equal to 6 factorial, because there are 6 possibilities of our unique first face, then 5 possibilities for our unique second face, so on and so forth, until there is only one face that has not been seen. Multiplying across all of these events, we get 6 factorial. Now let's compute the number of valid solutions. Remember that in order for a solution to be valid, we need to have first observed all the 3 even-numbered faces and then the odd-numbered faces. So, if we were to enumerate our 6 distinct values, these 3 must be some combination of 2, 4, or 6, and these last 3, some combination of 1, 3, and 5. These 2 sets make up our evens and our odds. And because we have evens before the odds, we get the title of this question. Now, by a very similar argument, we can count the number of ways to order these 3 evens to go in the first 3 slots, and we can count the number of ways to order the 3 odds to go in the last 3 slots. There are 3 possible values for our first even, 2 possible values for our second even, and our third slot right here must be the one remaining even. That is the number of ways to order our evens, and by the exact same logic, we can count the number of ways to order our odds. As you can see, this expression reduces to 3 factorial times 3 factorial. And this, in fact, is our numerator. So let's now bring this all the way back up here. 3 factorial times 3 factorial. Let's copy this entire expression so we can begin to do some reduction and get to a more concise solution. So this is equal to 3 times 2 times 1 divided by 6 times 5 times 4. And I made that logical step by canceling out that 3 factorial with the last three terms of this 6 factorial. This is equal to 2, doing a little bit of simplification, 1 over 20.
Thank you for watching. If you enjoyed the video, please like, subscribe, and check out our parent site, OpenQuant.co. Of course, if you have an alternative solution, please comment it below. We'll pin the best one. Thank you.